Through this opening, a river of charged particles races toward our planet at over 1 million miles per hour. Auroras dance across skies that have never seen them, and deep beneath our feet, something may be stirring. 2025 is already one of the most seismically active years on record. New research suggests the sun and earthquakes may be connected in ways we are only beginning to understand. The Carrington event of 1859 crashed telegraph systems worldwide. A storm of that magnitude today could knock out power for months, damage satellites, and cost trillions of dollars. NASA's Parker Solar Probe just flew closer to the sun than any object in human history. 430,000 miles per hour through temperatures of 1800 degrees. What it found is rewriting everything we thought we knew about our star. The sun is not quiet, the sun is not predictable, and the sun is pointed directly at us. Can we survive what our star might send our way, and who will pay the price if we cannot? Chapter 1: The Dark Wound on Our Star. But before we begin, do not forget to subscribe, and if you truly enjoy these videos, please leave a like. Let us begin. December 2025. The winter solstice. Half the world tilts away from the sun, wrapped in the longest night of the year, and somewhere above us, 93 million miles away, something strange is happening on the surface of our closest star. A wound has opened. Not a wound of blood or flesh, but a wound of absence. A vast dark region stretching across the face of the sun, visible only through specialized telescopes that capture ultraviolet light at 193 angstroms. To the untrained eye viewing these images, it looks like someone has torn a hole straight through our star. The darkness spreads from the northern hemisphere, slices through the solar equator, and plunges deep into the southern regions. Scientists call it a coronal hole, and this one, emerging in the final weeks of 2025, is among the largest observed in the 21st century. The numbers are staggering. 500,000 miles across. That is roughly 62 times the diameter of Earth. You could line up our entire planet 62 times and still not span the width of this dark void. Yet calling it a hole is somewhat misleading. The sun has not actually developed a gap in its surface. What we are witnessing is something far more fascinating and far more consequential for everyone living on the third rock from the sun. To understand what a coronal hole truly is, you must first understand the sun itself. Our star is not a solid ball. It is a churning sphere of plasma, a fourth state of matter where temperatures are so extreme that atoms lose their electrons and become electrically charged particles. At the core, where temperatures reach 27 million degrees Fahrenheit, hydrogen atoms fuse into helium, releasing the energy that powers all life on Earth. But the story of coronal holes begins much further out, in the outermost layer of the solar atmosphere called the corona. The corona is a region of contradiction. While the surface of the sun sits at roughly 10,000 degrees Fahrenheit, the corona somehow reaches temperatures of 2 to 3 million degrees. This mystery puzzled scientists for decades. How could the outer atmosphere be hundreds of times hotter than the surface below it? The answer lies in magnetic fields, those invisible lines of force that thread through the sun like a vast three-dimensional tapestry. When these magnetic field lines twist, snap, and reconnect, they release tremendous energy that heats the surrounding plasma to extraordinary temperatures. In most regions of the corona, these magnetic field lines form closed loops. They arc up from the solar surface, curve through space, and plunge back down again. The superhot plasma follows these loops, trapped by the magnetic architecture, glowing brightly in ultraviolet light. But in a coronal hole, something different happens. The magnetic field lines do not loop back. Instead, they stretch outward, extending deep into space like highways with no return. The plasma that would normally be trapped can now escape, flowing outward along these open magnetic channels at tremendous speeds. This is why coronal holes appear dark. They are not empty, they are depleted. The hot, glowing plasma that normally fills the corona has fled, streaming away from the sun as what we call the solar wind. What remains is cooler, less dense, and far dimmer than the surrounding regions. Through the specialized eyes of our space-based telescopes, these areas look like patches of shadow against the blazing face of our star. The coronal hole, now dominating the December sky, is what scientists call trans-equatorial. It does not simply sit near one of the sun's poles, as many coronal holes do during quiet periods. Instead, it cuts directly through the middle of the sun, crossing the solar equator like a dark river dividing two continents. This positioning matters enormously for Earth. Our planet orbits the sun along a plane called the ecliptic, roughly aligned with the solar equator. When a coronal hole opens near the poles, the high-speed solar wind it releases shoots off into space at angles that largely miss our world. But when a trans-equatorial hole opens and rotates to face Earth, we find ourselves staring directly down the barrel of a plasma cannon. The high-speed stream emerging from this December coronal hole travels at roughly 500 kilometers per second. That is over 1.1 million miles per hour. At this velocity, the solar wind reaches Earth in approximately 2 to 3 days, far faster than the normal solar wind that flows past our planet at more leisurely speeds. When this fast stream collides with our magnetic shield, the magnetosphere, the impact triggers what we call a geomagnetic storm. Right now, as you watch this video, instruments around the world are detecting the effects. Magnetometers in northern latitudes record fluctuations in Earth's magnetic field strength. The KP index, a measure of geomagnetic disturbance, scaled from 0 to 9, climbs to 5 or higher. The aurora oval, that ring of dancing lights encircling the polar regions, expands southward. People who have never seen the northern lights suddenly spot them from their backyards in Montana, Washington, and the upper Midwest. But the beauty masks potential danger. Our modern civilization runs on systems exquisitely vulnerable to space weather. Satellites orbiting Earth experience increased drag as the upper atmosphere swells with energy from geomagnetic storms. GPS signals degrade as the ionosphere becomes disturbed. High-frequency radio communications used by aircraft over polar routes black out for hours. Power grids experience voltage fluctuations as geomagnetically induced currents flow through their long transmission lines. In 1989, a geomagnetic storm knocked out power across Quebec, leaving 6 million people without electricity for 9 hours. That storm rated moderate on the scale of historical events. The coronal holes appearing during this solar cycle are generating conditions that could exceed anything we have experienced in the modern technological era. What makes the current situation particularly remarkable is timing. We are currently in solar cycle 25, the 25th 11-year cycle of solar activity since astronomers began systematic observations in 1755. Every 11 years or so, the sun's magnetic poles flip, and activity builds from a quiet minimum to an explosive maximum before declining again. Scientists initially predicted that solar cycle 25 would be weak, similar to the underwhelming cycle 24 before it. They were wrong. By October 2024, the sun had reached what NASA and NOAA officially declared as solar maximum, the peak of the cycle. Sunspot counts had exceeded predictions by significant margins. The strongest solar flares, massive explosions that release energy equivalent to billions of nuclear bombs, erupted with surprising frequency. And coronal holes, which typically become more common and larger during the descending phase after solar maximum, began appearing at unusual sizes while we were still climbing toward the peak. The December 2025 coronal hole is not an isolated phenomenon. Throughout this year, a series of gargantuan coronal holes have rotated across the sun's face, each one spraying Earth with high-speed solar wind streams. Some researchers are now questioning whether we have entered a particularly active period that could persist for years, perhaps continuing through the descent towards solar minimum around 2030. The implications extend beyond flickering lights and degraded GPS signals. Emerging research suggests connections between solar activity and processes deep within our own planet. Studies published in Nature and other prestigious journals have found statistically significant correlations between proton density in the solar wind and the occurrence of large earthquakes worldwide. The mechanism remains debated, but the data is increasingly difficult to ignore. When the sun sends charged particles streaming toward Earth, something responds within the crust and mantle below our feet. 2025 has already proven to be one of the most seismically active years on record. Coincidence? Perhaps. But the timing of earthquake swarms with solar wind impacts has raised eyebrows among researchers willing to investigate connections that mainstream science once dismissed as fringe speculation. We are learning that we live not on an isolated world, but within the extended atmosphere of a dynamic, sometimes violent star. The coronal hole staring at us right now is a reminder that 93 million miles offers less protection than we might hope. The sun sneezes, and Earth catches a cold. The sun opens a wound in its corona, and our satellites wobble, our power grids strain, our auroras dance, and perhaps even our tectonic plates shift. In the chapters ahead, we will dive deeper into this celestial drama. We will explore exactly how coronal holes form and why they matter. We will trace the history of the 11-year solar cycle back through centuries of observation. We will follow the solar wind on its journey from sun to Earth and examine what happens when it collides with our magnetic shield. We will revisit the Carrington event of 1859, the most powerful geomagnetic storm ever recorded, and ask what would happen if such an event struck today. We will investigate the controversial but growing body of evidence linking solar activity to earthquakes. We will journey alongside NASA's Parker Solar Probe as it flies closer to the sun than any human-made object in history. We will stand beneath the aurora and understand the physics that paints the night sky in greens, reds, and purples. And we will look toward the future, asking what our stormy star has in store for a civilization increasingly dependent on technologies that space weather can destroy. The dark wound on our star is not closing. If anything, the patterns suggest more and larger coronal holes in the years ahead as we descend towards solar minimum. Each one will send its river of charged particles washing over our world. Most of the time, our magnetic shield will hold. The disruptions will be minor. The auroras will be beautiful. But someday, perhaps soon, a coronal hole or coronal mass ejection will prove too powerful to dismiss. Understanding what is happening 93 million miles away has become essential knowledge for a technological species. The sun gives us life. It can also remind us, with humbling force, that we remain small creatures on a small world, subject to the whims of a star that has burned for 4.5 billion years and will continue burning for 4.5 billion more. The wound is open. Let us learn what it means. Chapter 2. What is a coronal hole? The name itself seems to contain a contradiction. How can the sun, that blazing sphere of nuclear fire, have holes? The answer requires us to abandon our earthly assumptions and think in terms of magnetic fields, plasma physics, and the strange behavior of matter at temperatures beyond anything we experience in daily life. Imagine for a moment that you could see magnetic fields, not with your eyes, which detect only a narrow slice of the electromagnetic spectrum, but with some enhanced sense that reveals the invisible architecture threading through space. If you looked at the sun with such vision, you would see something extraordinary. Lines of magnetic force erupting from the surface, curving through the corona, and diving back down again in graceful arcs. These closed loops trap plasma like invisible bottles, holding superhot gases in place and causing them to glow brilliantly in ultraviolet and X-ray wavelengths. But in certain regions, you would see something different. Lines of magnetic force that do not loop back. Instead, they stretch outward, reaching toward the stars, never returning. These are the open field regions, and the plasma here is not trapped. It flows outward along these magnetic highways at tremendous velocities, leaving behind a region that is cooler, less dense, and darker than its surroundings. This is what we call a coronal hole. The term was not always in use. Early astronomers studying the sun had no way to see these features directly. The corona itself was invisible except during total solar eclipses, those rare moments when the moon blocks the blinding solar disk and reveals the pearly white atmosphere surrounding it. Some eclipse photographs from the 19th and early 20th centuries hinted at darker regions near the poles, but without the ability to see in ultraviolet light, scientists could not understand what they were observing. The breakthrough came with the Skylab mission in 1973. For the first time, astronauts and instruments above Earth's atmosphere captured soft X-ray images of the sun with unprecedented clarity. There, unmistakably visible, were vast dark regions in the corona. Today we observe coronal holes routinely using spacecraft like NASA's Solar Dynamics Observatory, the ESA and NASA joint mission SOHO, and the newer GOES satellites that monitor space weather for the National Oceanic and Atmospheric Administration. These instruments capture images at specific wavelengths, particularly around 193 and 211 angstroms in the extreme ultraviolet range, where the contrast between normal corona and coronal holes is most striking. The physics of why coronal holes appear dark is elegant in its simplicity. The closed magnetic loops of the normal corona trap plasma at temperatures of 1 to 2 million degrees Kelvin, and this superheated gas radiates intensely in ultraviolet wavelengths. But in coronal holes, where the magnetic field lines open into interplanetary space, the plasma is free to escape. What remains is cooler, typically 700,000 to 1 million degrees Kelvin. Still unimaginably hot by earthly standards, but cool enough and sparse enough to appear dark compared to the surrounding corona. Think of it like a pot of boiling water with a lid versus one without. The lidded pot traps the steam, keeping the contents hot and roiling. Remove the lid, and the steam escapes. The pot cools. The coronal hole is the region where the magnetic lid has been removed, allowing the solar atmosphere to vent into space. Coronal holes come in different varieties, and understanding these distinctions helps explain their varying impacts on Earth. The most stable and long-lasting are polar coronal holes. These form near the north and south magnetic poles of the Sun and can persist for months or even years during periods of low solar activity. Because they are located at high solar latitudes, the high-speed solar wind they produce generally misses Earth, which orbits in the plane of the solar equator. More troublesome for our planet are equatorial coronal holes, and, especially, trans-equatorial coronal holes. These form at lower latitudes and can span the solar equator entirely. When such a hole rotates to face Earth, which happens as the Sun spins on its axis once every 27 days, the high-speed solar wind streams directly toward our world. The fast solar wind from these holes can persist for days or even weeks as the hole maintains its position relative to Earth during each solar rotation. There is also a category known as satellite holes. These are smaller coronal holes at lower latitudes that maintain magnetic connections to the larger polar holes through narrow corridors of open field lines. Satellite holes can produce variable fast solar wind streams that repeatedly sweep across Earth, complicating efforts to forecast space weather. The size of coronal holes varies enormously. Small holes may span only a few tens of thousands of miles. The giant trans-equatorial holes that have dominated recent space weather news stretch 500,000 miles or more. large enough to swallow dozens of Earths. Generally, larger holes produce faster and denser solar wind streams, which in turn cause more significant geomagnetic disturbances when they reach Earth. Coronal holes are intimately connected to the solar cycle. During solar minimum, when the sun is quiet and sunspots are rare, large polar coronal holes dominate. The magnetic field of the sun during these periods is relatively simple, with clearly defined north and south magnetic poles. The open field regions cluster near these poles, and the resulting high-speed solar wind flows primarily toward the outer solar system rather than toward Earth. As the sun approaches solar maximum, everything becomes more chaotic. The magnetic field grows increasingly complex as new active regions emerge. Sunspots dot the solar surface. The polar coronal holes may shrink or fragment, but intriguingly, equatorial and trans-equatorial coronal holes can appear, sometimes reaching enormous sizes even as overall solar activity increases. This is precisely what has surprised scientists during solar cycle 25. The giant coronal holes appearing in 2024 and 2025 were not expected at this stage of the cycle. After solar maximum, during the descending phase, coronal holes typically become more common and larger again. As the magnetic field simplifies and the new polarity establishes itself at the poles, open field regions expand. This period, lasting several years as the sun transitions toward the next minimum, often produces recurring high-speed solar wind streams that sweep past Earth with each solar rotation. The solar wind itself deserves closer examination. This continuous outflow of charged particles, predominantly protons and electrons, was predicted by the physicist Eugene Parker in 1958. Many of his colleagues were skeptical, but measurements from early spacecraft proved him correct. The solar wind streams outward in all directions from the sun, filling interplanetary space and creating what we call the heliosphere, a vast bubble of solar influence extending far beyond the orbit of Pluto. Not all solar wind is created equal. The slow solar wind, originating from regions of closed magnetic field, travels at roughly 300 to 400 kilometers per second. The fast solar wind, emerging from coronal holes, can reach speeds of 700 to 800 kilometers per second, or even higher. When these two streams interact, with faster wind overtaking slower wind ahead of it, complex structures called correlating interaction regions form. These regions can enhance the geomagnetic effects when they reach Earth. The plasma emerging from coronal holes carries embedded within it the magnetic field of the sun. This interplanetary magnetic field, as it is called, has polarity, meaning it points either toward or away from the sun depending on which hemisphere of the sun the wind originated from. Coronal holes also have polarity. A positive polarity hole has magnetic field lines pointing outward from the sun, while a negative polarity hole has field lines pointing inward. When the polarity of the incoming solar wind opposes Earth's own magnetic field orientation, a process called magnetic reconnection becomes more efficient, transferring more energy into our magnetosphere and producing stronger geomagnetic storms. Modern instruments on spacecraft like SOHO's solar wind, ion composition spectrometer, and the Advanced Composition Explorer have allowed scientists to study the chemical composition and temperature of solar wind from different sources. Fast solar wind from coronal holes shows distinct signatures: lower ionization states, reduced heavy ion abundances, and velocity distributions that reveal the acceleration mechanisms at work near the sun. The study of coronal holes has entered a new era with the Parker Solar Probe and Solar Orbiter missions. Parker has flown through coronal hole interiors during its close approaches to the sun, providing the first direct measurements of plasma conditions in regions where fast solar wind originates. The spacecraft has detected structures called switchbacks, dramatic reversals of the magnetic field that suggest complex dynamics in the acceleration of solar wind. Solar Orbiter, with its suite of remote sensing instruments, has revealed small-scale jets called picoflares within polar coronal holes that may contribute to both the heating of the corona and the acceleration of the solar wind. Despite decades of study, mysteries remain. Why does the corona reach temperatures hundreds of times hotter than the solar surface? Exactly what mechanisms accelerate the fast solar wind to such extreme velocities? How do coronal holes form and evolve? What determines whether a coronal hole will remain stable for months or disappear within days? These questions drive ongoing research programs at observatories and space agencies around the world. Planned missions like NASA's Multi-Slit Solar Explorer, expected to launch around 2027, will study the corona using advanced spectrographic techniques to measure plasma temperature, speed, and turbulence at unprecedented resolution. Understanding coronal holes and the solar wind they produce is essential for predicting space weather with enough accuracy to protect our satellites, power grids, and astronauts. For those of us watching from Earth, coronal holes present a fascinating duality. They are absences, regions where something is missing, plasma that has fled, light that has dimmed, yet their effects are profoundly present. When a giant coronal hole rotates to face our world, we feel its influence in disrupted communications, stressed power systems, expanded auroral zones, and perhaps even trembling faults deep beneath our feet. The dark patch on the sun is not truly a hole. It is a doorway, an opening through which our star breathes its atmosphere into space. And when that breath is pointed at us, we would do well to pay attention. Chapter 3: The 11-Year Heartbeat. Long before humans understood that the sun was a star, long before we knew about magnetic fields or nuclear fusion, careful observers noticed something peculiar. Dark spots appeared on the face of the sun, grew, shifted position, and eventually faded away. The Chinese recorded such observations as early as 800 BCE. Greek philosophers debated what these blemishes might mean for a celestial body thought to be perfect and unchanging. But it was not until the early 17th century, when Galileo turned his telescope toward the sun, that systematic study of sunspots began. What Galileo saw challenged everything Europe believed about the heavens. Dark patches, irregular in shape, moving across the solar disk as the sun rotated. Some lasted weeks before vanishing. Others appeared suddenly in regions that had been clear days before. The sun was not a flawless sphere of divine fire. It was dynamic, changeable, subject to forces no one yet understood. Over the following centuries, astronomers accumulated observations. The German pharmacist Samuel Heinrich Schwabe spent 17 years obsessively tracking sunspots, drawing the solar disk day after day between 1826 and 1843. His persistence revealed a pattern no one had suspected. Sunspot numbers rose and fell in a regular rhythm, peaking roughly every 10 years before declining to minimum levels. Schwabe had discovered the solar cycle. Further refinements pinpointed the average length at approximately 11 years, though individual cycles vary from as short as 9 years to as long as 13. The Swiss astronomer Rudolf Wolf standardized methods for counting sunspots and reconstructed historical records back to 1755, which marks the beginning of solar cycle 1. We are now in solar cycle 25, which began in December 2019 and will likely continue until around 2030. But what causes this 11-year heartbeat? Why does our star pulse between quiet phases with few or no sunspots and active phases where the solar surface erupts with dozens of dark patches, explosive flares, and billion-ton ejections of plasma? The answer lies in the sun's magnetic field and its extraordinary behavior. Unlike Earth, which has a relatively stable magnetic field generated by its solid iron core and liquid outer core, the sun generates its magnetic field through a process called the solar dynamo. The sun is not solid. It is a sphere of plasma that rotates, and it does not rotate uniformly. The equator completes one rotation in about 25 Earth days, while regions near the poles take closer to 35 days. This differential rotation stretches and twists magnetic field lines that initially run from pole to pole. Imagine taking a rubber band stretched between the top and bottom of a spinning sphere, then spinning the middle faster than the ends. The band would wrap around the equatorial regions, becoming increasingly wound and distorted. This is essentially what happens to the Sun's magnetic field. Over years, the poloidal field, running from north to south, transforms into a toroidal field, wrapped around the Sun's interior like coils around a cylinder. These concentrated magnetic field lines eventually become unstable. They rise buoyantly through the solar interior, puncturing the surface in paired loops that we observe as sunspot groups. Sunspots appear dark because the intense magnetic fields within them suppress convection, preventing hot plasma from welling up from below. The result is a region roughly 3,000 degrees cooler than the surrounding photosphere. Cool enough to appear black by contrast, though still blazing at nearly 7,500 degrees Fahrenheit. The magnetic polarity of sunspot pairs follows predictable rules discovered by American astronomer George Ellery Hale in the early 20th century. In each hemisphere, the leading sunspot in a pair, the one ahead in the direction of rotation, has a consistent polarity throughout a given cycle. The trailing spot has the opposite polarity. Furthermore, this orientation is reversed between the northern and southern hemispheres. If northern leading spots are positive in one cycle, southern leading spots will be negative. And here is where the story becomes even more remarkable. When the next 11-year cycle begins, everything flips. Leading spots in the north that were positive become negative. Southern leading spots switch from negative to positive. The Sun's entire magnetic polarity is reversed. What was the magnetic North Pole is now the magnetic South Pole, and vice versa. This means that the true cycle of the Sun's magnetic field is not 11 years, but roughly 22 years. After 2 activity cycles, the Sun returns to its original magnetic configuration. This 22-year period is sometimes called the Hale cycle, honoring the scientist who discovered the polarity rules. Solar maximum refers to the period when sunspot numbers peak and solar activity is most intense. During maximum, the Sun's magnetic field is chaotic, with field lines tangled across multiple active regions. Flares become frequent and powerful. Coronal mass ejections blast billions of tons of plasma into space. The corona itself changes shape, becoming more irregular as streamers and active region loops dominate the view. Solar minimum is the quiet phase. Sunspots may be entirely absent for weeks or months. The magnetic field simplifies, with clear polar regions of opposite polarity. Coronal holes expand near the poles. The corona takes on a more symmetric appearance. Solar flares and coronal mass ejections become rare. The transition from minimum to maximum takes approximately 4 to 5 years. Activity builds gradually at first, then accelerates. New sunspots appear at higher latitudes, then migrate toward the equator as the cycle progresses. A pattern visualized in what scientists call the butterfly diagram, because the latitude versus time plot of sunspot positions resembles a butterfly's wings. The transition from maximum back to minimum also takes several years, but tends to be more gradual. The descending phase is notable for the increasing prominence of coronal holes, particularly equatorial ones that can persist through multiple solar rotations. This is the period when recurring high-speed solar wind streams are most common, sweeping past Earth every 27 days as the same coronal hole rotates back into geoeffective position. Not all solar cycles are created equal. Some maximums produce far more sunspots and intense activity than others. Scientists use the smoothed sunspot number, a 13-month average that reduces short-term fluctuations, to compare cycle strength. The strongest cycle on record was cycle 19, which peaked in 1958 with a smoothed sunspot number exceeding 200. The weakest in the modern era was cycle 24, which peaked in April 2014 with a maximum around 116, well below the historical average of approximately 179. The prediction for solar cycle 25, released by an international panel convened by NOAA, NASA, and the International Space Environmental Services in December 2019, forecast another weak cycle with a maximum of about 115 sunspots around July 2025. This prediction fit within the trend of weakening cycles that had characterized cycles 21 through 24. Some researchers even speculated that the Sun might be heading toward a grand minimum, an extended period of very low activity, like the Maunder minimum of 1645 to 1715, when sunspots nearly disappeared for 70 years. The prediction was wrong. By 2022, just 2 years into the cycle, observed sunspot numbers were already exceeding forecasts. Activity ramped up faster than anyone expected. By October 2023, NOAA issued a revised prediction calling for an earlier and stronger peak, possibly reaching smoothed sunspot numbers between 137 and 173, sometime between January and October 2024. In October 2024, NASA and NOAA officially declared that the Sun had reached solar maximum. The smoothed sunspot number had climbed to approximately 161. Solar cycle 25 was not just stronger than predicted. It had proven to be significantly more active than its predecessor. Cycle 24, the surprises continued. Even after the official declaration of maximum, activity remained high. In November 2025, the Sun unleashed an X5.16 solar flare, the strongest of the cycle and the sixth most powerful in all of solar cycle 25. Coronal holes that should have been more typical of the descending phase appeared at enormous sizes while the Sun was still near peak activity. Scientists now debate whether we have truly passed the maximum or whether solar cycle 25 might produce a secondary peak. Some cycles in history have exhibited double maxima, with two distinct peaks of activity separated by a year or more. The data through late 2025 shows hints that this could be occurring, though only time will reveal the true shape of the cycle. Why does any of this matter beyond academic curiosity? Because the solar cycle controls the rhythm of space weather that affects our planet. During solar maximum, geomagnetic storms become more frequent and more intense. The radiation environment in space becomes more hazardous for astronauts and spacecraft electronics. Satellite operators face increased drag and debris tracking challenges. Power grid operators must be vigilant for geomagnetically induced currents. Airlines reroute polar flights to avoid radiation exposure and communication blackouts. Conversely, during solar minimum, the risks diminish but do not disappear. Cosmic rays from outside the solar system penetrate more easily when the Sun's magnetic field is weak, slightly increasing radiation exposure at high altitudes. And the coronal holes that grow during the descending phase and minimum continue producing high-speed solar wind streams that can trigger geomagnetic storms. Even when the Sun seems quiet, the 11-year heartbeat of our star is not merely an astronomical curiosity. It is a rhythm that shapes the space environment in which our entire technological civilization exists. Understanding it, predicting it, and preparing for its variations has become essential for a species that has wrapped itself in satellites, power grids, and global communication networks. The Sun will continue pulsing through its cycles for billions of years to come. Our challenge is to learn its rhythms well enough to dance safely within them. Chapter 4: Solar Wind and the Invisible River. In 1958, a young physicist named Eugene Parker proposed something radical. He suggested that the Sun was not simply radiating light and heat into an empty void. Instead, it was exhaling, continuously streaming charged particles outward at tremendous velocities, filling the entire solar system with a thin but constant flow of solar material. He called this flow the solar wind. His colleagues were skeptical. Some were hostile. The idea that plasma could continuously escape the sun's gravity and pervade interplanetary space seemed to contradict thermodynamic principles. One prominent scientist recommended that Parker's paper be rejected from publication, but the editor chose to publish it anyway, and within 4 years, the Soviet Luna 1 and American Mariner 2 spacecraft confirmed that Parker had been right all along. The solar wind is real. It is everywhere, and it fundamentally shapes the space through which all planets move. To understand the solar wind, you must first appreciate the extraordinary temperatures of the solar corona. While the visible surface of the sun, the photosphere, registers at roughly 5,500 degrees Celsius, the corona reaches temperatures of 1 to 3 million degrees Celsius. At such extreme temperatures, the thermal energy of particles exceeds the gravitational binding energy of the sun. They can escape, and escape they do, in numbers beyond ordinary comprehension. Every second, the sun loses approximately 1 million tons of material to the solar wind. That sounds like an enormous amount, and it is by any human measure, but the sun contains roughly 2,000 trillion tons of matter. At the current loss rate, it would take 150 billion years for the solar wind to carry away even 1% of the sun's mass. Our star can afford to be generous with its outflow. The composition of the solar wind reflects the composition of the sun itself. Approximately 95% consists of protons, the nuclei of hydrogen atoms. Another 4% comprises alpha particles, which are helium nuclei containing 2 protons and 2 neutrons. The remaining 1% includes heavier ions, electrons, and trace amounts of other elements. All of these particles carry electrical charge, making the solar wind a plasma, an electrically conductive gas threaded with magnetic field lines. Those magnetic field lines are crucial. As solar wind plasma streams outward from the sun, it carries embedded within it the magnetic field of the solar corona. This interplanetary magnetic field, often abbreviated IMF, does not simply point straight outward. Because the sun rotates while the plasma flows outward, the field lines curve into a spiral pattern, like water spraying from a spinning garden sprinkler. This is called the Parker spiral, named after the same Eugene Parker who predicted the solar wind. At Earth's orbit, 93 million miles from the sun, the Parker spiral makes an angle of roughly 45 degrees with respect to the Sun-Earth line. The magnetic field lines have wound around enough to be significantly tilted from the radial direction. This geometry matters because the orientation of the interplanetary magnetic field strongly affects how the solar wind interacts with Earth's magnetosphere. Not all solar wind travels at the same speed. Slow solar wind, typically originating from regions of closed magnetic loops near the sun's equator, moves at 300 to 400 kilometers per second. Fast solar wind, streaming from coronal holes where magnetic field lines open directly into space, can reach 600 to 800 kilometers per second, or even faster. At these velocities, it takes the slow solar wind 4 to 5 days to reach Earth. Fast solar wind can arrive in 2 to 3 days. When fast solar wind catches up with slow solar wind ahead of it, the two streams interact, creating compressed regions of higher density and stronger magnetic fields called corrotating interaction regions. These structures spiral through the solar system along with the Parker spiral and can enhance geomagnetic effects when they sweep past Earth. During the descending phase of the solar cycle, when coronal holes are common and persistent, corrotating interaction regions become a regular feature of space weather. The solar wind does not stop at Earth. It continues outward, past Mars, past Jupiter, past Saturn, beyond the orbit of Pluto, until it finally encounters the interstellar medium, the thin gas and dust between the stars. This boundary region is called the heliopause, located roughly 120 astronomical units from the Sun, or about 11 billion miles. Within this vast bubble, called the heliosphere, the solar wind dominates. Beyond it lies interstellar space, territory explored only by the Voyager 1 and 2 spacecraft. The solar wind creates and maintains this heliosphere, a protected zone within the galaxy. Cosmic rays, high-energy particles accelerated by distant supernovae and other violent events, constantly bombard the heliosphere from outside. The magnetic field carried by the solar wind deflects and modulates many of these cosmic rays, reducing the radiation environment throughout the solar system. When solar activity is high and the solar wind is strong, fewer cosmic rays penetrate to Earth's orbit. When solar activity is low, more get through. But it is the interaction with Earth's magnetic field that most directly affects human technology and safety. Earth is surrounded by a magnetosphere, a region of space dominated by our planet's magnetic field. This field is generated deep within Earth's core, where the rotation of liquid iron creates a dynamo effect, similar in principle to the Sun's dynamo, but operating on vastly different scales. The magnetosphere extends tens of thousands of miles into space on the day side, facing the Sun, and stretches into a long tail millions of miles long on the night side. When the solar wind arrives at Earth, it cannot simply penetrate the magnetosphere. Plasma cannot easily cross magnetic field lines. Instead, the solar wind flows around the magnetosphere, like water around a rock in a stream. On the sunward side, it compresses the magnetosphere, pushing the boundary, called the magnetopause, closer to Earth. On the nightward side, it stretches the magnetosphere into an elongated tail. The pressure of the solar wind determines the position of the magnetopause. Under normal conditions, this boundary sits roughly 10 Earth radii from the surface, about 40,000 miles. During periods of high solar wind pressure, such as when a high-speed stream from a coronal hole impacts Earth, the magnetopause can be pushed inward to 6 Earth radii or less. Satellites in geostationary orbit, approximately 22,000 miles up, can find themselves momentarily outside the protection of the magnetosphere. The most significant factor in solar wind magnetosphere interaction is not the speed or density of the incoming plasma, but the orientation of the interplanetary magnetic field. Earth's magnetic field points northward at the equator, from South Pole toward North Pole. When the interplanetary magnetic field has a southward component, opposing Earth's field, a process called magnetic reconnection can occur. Magnetic reconnection is a fundamental process in plasma physics. When two magnetic field lines of opposite polarity meet, they can break and reconnect in new configurations, releasing tremendous amounts of energy. At Earth's dayside magnetopause, reconnection between southward interplanetary magnetic field and northward terrestrial field opens a pathway for solar wind energy to enter the magnetosphere. This energy flows along magnetic field lines toward the poles, energizes particles in the radiation belts, and ultimately drives the phenomena we call geomagnetic storms. The KP index, mentioned in earlier chapters, is one measure of geomagnetic activity resulting from solar wind magnetosphere interaction. It is calculated from magnetometer observations at stations around the world, tracking fluctuations in the magnetic field caused by electrical currents in the magnetosphere and ionosphere. The index runs from 0, indicating very quiet conditions, to 9, indicating extreme storm levels. NOAA's Space Weather Prediction Center uses a simpler 5-level scale for geomagnetic storms, ranging from G1 for minor storms to G5 for extreme storms. Each level corresponds to specific ranges of the KP index and carries different implications for technology and infrastructure. A G1 storm might cause minor power grid fluctuations and slightly expand the auroral zone, A G5 storm could cause widespread power outages, damage transformers, disrupt satellite operations, and produce auroras visible from tropical latitudes. The solar wind is thus far more than an astronomical curiosity. It is a medium through which our star constantly interacts with our planet. Every moment of every day, Earth swims through this invisible river of charged particles. Most of the time, our magnetic shield deflects the flow with ease. But when the solar wind intensifies, when a high-speed stream from a coronal hole or a shock wave from a coronal mass ejection arrives, the interaction can become violent. Eugene Parker, who passed away in 2022 at age 94, lived to see his theoretical prediction confirmed beyond any doubt. He saw spacecraft venture into the solar wind and measure its properties directly. He witnessed the launch of the Parker Solar Probe, the first NASA mission ever named for a living person, which now flies closer to the Sun than any human-made object in history. The invisible river continues to flow. It has flowed for 4.5 billion years, since the Sun first ignited in the collapsing cloud of gas and dust that formed our solar system. It will continue flowing for billions of years more, until the Sun exhausts its hydrogen fuel and swells into a red giant, ultimately shedding its outer layers and becoming a white dwarf. For now, we learn to read the river's currents and predict its floods. The solar wind carries the breath of our star to every corner of the heliosphere. Understanding that breath and respecting its power is no longer optional for a technological civilization. It is essential. Chapter 5. When the Shield Falters. On March 13th, 1989, the Sun hurled a massive cloud of plasma and magnetic field toward Earth. The coronal mass ejection traveled through interplanetary space for 3 days before slamming into our planet's magnetosphere with devastating force. Within 90 seconds of the impact, 6 million people in Quebec lost electricity as the Hydro-Quebec power grid collapsed. Transformers overloaded. Circuit breakers tripped in cascading failures. The province went dark. For 9 hours, hospitals switched to backup generators. Traffic signals failed. Heating systems shut down on a night when temperatures plunged well below freezing. Schools closed. Businesses halted. A modern society discovered just how vulnerable it had become to events 93 million miles away. The March 1989 geomagnetic storm was severe, but it was not exceptional by historical standards. It registered approximately -589 nanoteslas on the DST index, a measure of the depression in Earth's magnetic field caused by ring current intensification during storms. This placed it among the strongest storms of the 20th century, but nowhere near the strongest ever recorded. That distinction belongs to events from an era before our technological dependencies made space weather a matter of critical concern. Yet even in 1989, the Quebec blackout demonstrated that modern infrastructure exists within the reach of solar fury. To understand how geomagnetic storms damage power grids and disrupt technology, we must examine what happens when the solar wind magnetosphere interaction intensifies beyond normal levels. Under ordinary conditions, Earth's magnetic field deflects most of the solar wind around the planet. Magnetic reconnection occurs at modest rates, and the energy entering the magnetosphere dissipates. But when a coronal mass ejection arrives, or when a particularly fast and dense solar wind stream from a coronal hole impacts the magnetopause, the dynamics change dramatically. Coronal mass ejections are fundamentally different from the steady solar wind. These are explosive releases of billions of tons of plasma and tangled magnetic field, blown outward from the Sun at velocities ranging from a few hundred to over 2,000 kilometers per second. The fastest CMEs can reach Earth in under 24 hours. A typical transit takes 2 to 3 days. When they arrive, they often carry magnetic fields much stronger than the ambient solar wind. And these embedded fields can be oriented strongly southward, maximizing the conditions for magnetic reconnection. The arrival of a CME at Earth occurs in stages. First comes the shock wave, the boundary where the fast-moving CME plasma has compressed the slower solar wind ahead of it. This sudden compression pulse causes what is called a storm sudden commencement, a sharp increase in the magnetic field strength recorded at ground stations worldwide. The magnetosphere is squeezed, and currents flowing in the magnetopores intensify. Behind the shock comes the sheath region, the turbulent zone of compressed plasma between the shock and the CME proper. Sheath regions often contain highly variable magnetic fields, including southward components that can drive reconnection and storm development even before the main CME structure arrives. Finally comes the magnetic cloud, or ejector itself, the core of the CME. This region typically shows smoothly rotating magnetic fields and lower plasma temperatures. If the magnetic field within the cloud is oriented southward for extended periods, it can drive prolonged and intense geomagnetic storming. As reconnection proceeds on the dayside magnetopores, magnetic flux is transferred to the nightside magnetotail. Energy accumulates in the tail until instabilities cause explosive reconnection there as well, releasing the stored energy into the inner magnetosphere. Particles are accelerated to high energies and injected into the ring current, a belt of charged particles encircling Earth at distances of 3 to 8 Earth radii. The ring current creates its own magnetic field, opposing Earth's field at low latitudes. This is what the DST index measures. During intense storms, the ring current can become so strong that it measurably reduces the surface magnetic field by hundreds, or even over 1,000 nanoteslas. The depression in field strength indicates the energy that has been pumped into the magnetosphere from the solar wind. Meanwhile, currents also flow in the ionosphere, the electrically conducting layer of Earth's upper atmosphere. Auroral electrojets, intense horizontal currents flowing in the auroral zones, can exceed millions of amperes during major storms. These rapidly varying currents induce electric fields at Earth's surface through electromagnetic induction, the same principle that makes transformers work. Here is where human infrastructure becomes vulnerable. Long conductive networks like power lines act as antennas for these induced electric fields. Currents called geomagnetically induced currents, or GICs, flow through the grounded neutrals of transformers, seeking paths through the power grid. These are quasi-direct current flows, very different from the alternating current the grid is designed to handle. Transformers are particularly susceptible. GICs can saturate transformer cores, causing them to operate inefficiently, generate excess heat, and produce harmonic distortions in the power signal. In mild cases, this simply degrades power quality. In severe cases, transformers can overheat and suffer permanent damage. The failure of even a few critical transformers can cascade through interconnected grids, causing widespread blackouts. The Quebec collapse in 1989 demonstrated this vulnerability dramatically. Within 90 seconds of the storm's intensification, relays tripped across the Hydro-Quebec system. The utility had no time to respond. The province's grid was down before operators fully understood what was happening. Recovery took hours. Had more transformers been permanently damaged, recovery could have taken weeks or months. Modern power grids have implemented some protections since 1989. Operators monitor space weather forecasts and can take precautions during predicted storms, such as cancelling maintenance, increasing reserves, and preparing for potential load shedding. Some utilities have installed GIC blocking devices on vulnerable transformers, but the fundamental vulnerability remains. A sufficiently powerful storm will overwhelm existing protections. Power grids are not the only concern. Geomagnetic storms affect satellites in multiple ways. Enhanced radiation levels can damage sensitive electronics and degrade solar panels. Increased atmospheric drag at low Earth orbit altitudes causes satellites to lose altitude faster than expected. Thousands of satellites now fill low Earth orbit, including mega constellations like Starlink. During the May 2024 geomagnetic storm, one of the strongest in decades, satellite operators reported significant increases in drag and the need for coordinated maneuvering to avoid collisions. GPS and other global navigation satellite systems rely on precisely timed radio signals passing through the ionosphere. Geomagnetic storms disturb the ionosphere, introducing errors that degrade positioning accuracy. During the 1989 storm, GPS errors reportedly exceeded normal levels significantly. Aviation authorities issued warnings about reduced navigation reliability. High-frequency radio communications, used by aircraft over oceanic and polar routes, can be completely blocked during major storms. When the ionosphere is severely disturbed, radio signals that normally reflect off this layer and travel beyond the horizon instead become absorbed or scattered. Aircraft lose contact with ground controllers. Emergency communications become unreliable precisely when they might be most needed. The radiation environment in space intensifies during geomagnetic storms.